Now, in this lecture, we'll answer two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we'll find out the value of the green area that is inside a quarter circle. So we'll start with the first question. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. We know that line segment PD equals to 5 units. Angle TBC equals to 30 degrees. And our mission is to find out the area of this circle. Okay, so first of all, we'll define the center of this circle as O. We will join here, and the point of tendency of tangent AB with this circle is point Q. So we'll join points Q and O together by a straight line. Point O is the center of the circle, point Q is the point on the circle itself, therefore OQ is the radius of this circle that we define as R. And we have the radius OQ that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we'll join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that is equal to R. And again, we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We also know that all the angles inside square ABCD are right angles, so this angle equals to 90 degrees. This angle, it is also equal to 90 degrees, equals to 90 degrees. This angle is equal to 90 degrees, and finally, this angle is equal to 90 degrees. So, actually, inside quadrilateral AQPO, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees plus the size of the fourth angle. In total, they must be equal to 360 degrees. Therefore, the fourth angle must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So we found out that inside quadrilateral AQPO we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. AQ equals to PO. But we have already found out that PO equals to R. And from this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. AQ equals to R. So here, AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. AP equals to QO, but we have already found out that QO equals to R, it is the radius of the circle. And from this equation, AP equals to QO equals to R, we will derive that AP is also equals to R. AP equals to R. Therefore, we actually found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. Okay, quadrilateral AQPO is a square. We also know that all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. Side AD equals to side AB. AD equals to AB. I'll repeat again. In square ABCD, side AD equals to side AB. What is the length of side AD? It is very easy to say from the drawing that AD equals to R plus 5. What is the length of side AB? AB equals to R plus QB. In conclusion, we found out that R plus 5 equals to R plus QB. Here we'll subtract R from this equation and we get that R will get cancelled, that 5 equals to QB, or QB equals to 5 units. Here, QB equals to 5 units. In the next step, I will present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. We have the common extreme point P. From the common extreme point P, we have tangent PA to this circle and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. We can implement rule number 2 in our drawing. Here, if we focus on the common extreme point B, from the common extreme point B, we have two tangents to this circle. We have tangent BQ, and we also have here, we define the point of tendency of tangent BT with this circle as S. And the second tangent from the common extreme point B is tangent BS. And according to rule number 2, BQ equals to BS. So repeat again. According to rule number 2, BQ equals to BS. Okay, but we have already found out that BQ equals to 5 units, so we can write here that BQ equals to 5 units. And for this equation, 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units. Here BS equals to 5 units. In the next step, we'll join points Q and S together by a straight line. By joining points Q and S by a straight line, we created there triangle QBS. What is the size of angle QBS? The size of angle QBS will be angle ABC, the big angle that is equal to 90 degrees, minus angle TBC that is equal to 30 degrees. That is to say, 90 degrees minus 30 degrees, it is 60 degrees. So angle QBS equals to 60 degrees in its size. We'll focus on triangle QBS. In triangle QBS, those two sides are equal to, they are both equal to 5 units, therefore they are equal to each other. That is to say, side BS equals to side BQ. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if we define this angle as alpha, then this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be also equal to each other. Okay, so those two angles, they are both equal to alpha. This angle, will continue to focus on triangle QBS. This angle equals to 60 degrees. Therefore, the sum of the other two angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. I write it down in triangle QBS. Alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. Here we divide this equation by 2, and we get that angle alpha equals to 120 degrees over 2, that is 60 degrees. So we found out that this angle alpha equals to 60 degrees. And this angle alpha equals to 60 degrees. So therefore, in triangle QBS, all the angles are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Triangle QBS is an equilateral triangle. Because of the fact that all of its angles are equal to 60 degrees, it is an equilateral triangle. And we know that in equilateral triangle, all the sides are equal to each other. that is to say side QB that is 5 units equals to side BS that is also 5 units, therefore the missing side QS must be also equal to 5 units. Here, side QS equals to 5 units. In the next step, we'll join points O and S together by a straight line. Okay. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of the circle that is equal to R. In the next step, I will present to you the law of cosines and we will implement the law of cosines in the green triangle QOS. So what is the law of cosines? The law of cosines is true in any triangle. So if we have triangle ABC that could be any triangle, this is triangle ABC. This is triangle ABC. In triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again on the law of cosines. According to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay. Now we'll implement the law of cosines in the green triangle QOS. So I copy triangle QOS in this new page and we'll implement the law of cosines in this triangle. But before we implement the law of cosines in the green triangle QOS, we'll focus on quadrilateral OSBQ. So I copy quadrilateral OSBQ in the new page and we'll analyze quadrilateral QOSB. Here we have the radius OS that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees. This angle also equals to 90 degrees. So angle OSB equals to 90 degrees. Angle OQS, it is also equals to 90 degrees according to rule number 1. So actually, this is quadrangle QBOS that I copied from the original drawing. What is the size of the missing angle? This missing angle. The size of the missing angle will be equal to the sum of the angles in quadrangle QBOS, that is 360 degrees, minus the sum of 3 other angles that are known, minus this angle that is 90 degrees, plus this angle that is also 90 degrees, plus this angle that is equal to 60 degrees. So 360 degrees minus the sum of the 3 other angles must be equal to the size of the missing angle, angle QOS. Okay. So the missing angle QOS will be equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees. 180 degrees plus 60 degrees is 240 degrees. And 360 degrees minus 240 degrees is 120 degrees. So we found out that the missing angle QOS is equal to 120 degrees. This angle equals to 120 degrees. So here angle QOS equals to 120 degrees. Okay. Now we'll implement the law of cosines in this triangle QOS. Angle QOS equals to 120 degrees, QO equals to R, OS also equals to R, they are both the radii of the circle. And we already found out that QS equals to 5 units. So we will implement the law of cosines in triangle QOS. According to the law of cosines, we will get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 square is 25. That is equal to r square plus r square is 2r square minus 2 times r is minus 2r square, and cosine 120 degrees is minus 1 over 2, minus 1 half. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, we found out that $25 equals to 2r square plus r square is 3r square. So here we divide this equation by 3 and we get that r square equals to 25 over 3. We know that the area of any circle is equal to pi r square. But we have already found out that r square equals to 25 over 3, therefore we can substitute r square in this formula by 25 over 3. So we'll do it now and we get that the area of our circle equals to pi times 25 over 3. R square is 25 over 3, so it is pi times 25 over 3. In conclusion, we found out that the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. I'll repeat again, the area of this circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. We finish with the first question. In the next step, I will present to you the second question and we'll solve the second question in 3 different methods. So, in the drawing, we have a quarter circle. Inside the quarter circle, we have a small circle. And we know that line segment CD equals to 8 units in length. And this angle ACD equals to 90 degrees. And our mission is to find out the value of the area of the green shape. Okay, so we'll start with the first method, and we will define the center of the small circle as J. We'll define the point of tendency of tangent CD with the small circle as E. We define the point of tendency of tangent OB with a small circle as F. We will join points J and E together by a straight line. Point J is the center of the small circle, point E is the point of the circle itself, therefore JE is the radius of the circle that we will define as R. We have the radius JE that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join points J and F together by a straight line. Point J is the center of the circle, point F is the point of the circle itself. Therefore JF is the radius of the small circle that is equal to R. We have the radius JF that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. And because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle, and angle AOB, this angle, must be equal to 90 degrees. And also AO must be the radius of the quarter circle that we will define as capital R. Okay? And AO as a radius, as a radius of the quarter circle, it is absolutely a straight line. Okay, AO as a radius must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. Okay, so which angles we have at this side of AO at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be equal to 90 degrees. In the next step, we will join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle that is equal to capital R according to our definition. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. Okay? So, according to the Pythagoras theorem, the right green triangle, triangle OCD, here by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle OCD is OD. Therefore, the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO squared plus CD squared. Okay, according to the Pythagoras theorem, OD squared equals to CO squared plus CD squared. Before we will continue, we will find out the length of CO. From the center of the small circle, that is to say from point J, we will go perpendicular on CO. So here this angle equals to 90 degrees. And this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So here inside quadrilateral CFTJ, the upper small quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Likewise, inside the lower quadrilateral TJOF, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So we found out that angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. Angle EJF equals to 180 degrees. Therefore, angle EJF is a straight line. If angle EJF is a straight line, then line segment EJF is also a straight line. And if line segment EJF is a straight line, then EF itself is also, line segment EF is also a straight line. EF is also a straight line. And if line segment EF is a straight line, it means that quadrilateral CEOF, this quadrilateral, is a rectangle. I write it down, quadrilateral CEOF is a rectangle. Why it is a rectangle? Because of the fact that inside quadrilateral CEOF we have 4 right angles. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF. But we have already found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. CO equals to 2R. Here, CO equals to 2R. Now we continue with the implementation of the Pythagoras theorem on the green right triangle, triangle COD. According to the Pythagoras theorem, in the right triangle OCD, the right green triangle, OD square equals to CO square plus CD square. OD, the hypotenuse OD equals to capital R, therefore OD square is capital R square. That is equal to CD square. CD equals to 2R, therefore CD square is 2R square, that is 4R square, plus, is actually CO square. CO equals to 2R, therefore CO square equals to 2R square, that is 4R square, plus CD square. CD equals to 8 according to what is given as the equation, therefore CD square is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. We subtract 4R square from this equation number 1, and we get that according to equation number 1, capital R square minus 4R square equals to 64. We found out that according to equation number 1, capital R square minus 4R square equals to 64. But what is actually the area of the green shape? It is very easy to see from the drawing that the area of the green shape is equal to the area of the quarter circle minus the area of the small circle. repeat again. The area that we are looking for, that is the area of the green shape, equals to the area of the quarter circle minus the area of the small circle. What is the area of the quarter circle? The area of the quarter circle, it is equal to pi times capital R square over 4. It is the area of the circle over 4. It is pi times capital R square over 4. What is the area of the circle? It is very simple. It is equal to pi R square. So here we take pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4? We took from it pi over 4 as a common factor. What is left is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4 times R squared. Why? Because minus 4 times R squared times pi over 4 equals exactly to minus pi R squared. So here we found out that we have the expression that capital R squared minus 4R squared, but we only found out that capital R squared minus 4R squared equals to 64. Therefore we can substitute capital R squared minus 4R squared by 64. We'll do it now, and we get that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So I found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, so we finished the first method. The next step, I'll present to you the second method to find out the area of this green shape. In the second method, we use for the things that we have only found out in the first method. In the first method, we have only found out that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. This angle equals to 90 degrees. This angle it is also equal to 90 degrees. What is the length of line segment AC? AC, from the drawing it is very easy to see that AC equals to AO minus CO. Again, AO minus CO equals to AC. So it is AO minus CO. That is to say, AC equals to AO, that is capital R, the radius of the quarter circle, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. In the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we'll extend the radius AO by straight line until it intersects with the circle. We define the touching point of the extended radius AO and the circle as point T. So point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. In the next step, we will extend the straight line DC by straight line until it intersects with the circle. And we define the touching point of the extended straight line DC and the circle as point M. So we extended the straight line DC by straight line. When you extend the straight line by straight line, the result must be a straight line. So DM is a straight line. DM is a straight line, so if you focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of DM at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees in order to complete the sum of the angles in the lower side of the straight line DM to 180 degrees. This angle must be also equal to 90 degrees. In the next step, we join points M and O together by a straight line. Point O is the center of the big circle, point M is the point of the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. Likewise, we join points O and D together by a straight line. Point O is the center of the big circle, point D is the point of the big circle itself, therefore OD is the radius of the big circle that is also equals to capital R. Okay. So in the next step, we prove that the two right triangles, triangle MCO and triangle COD, can go into each other. So I write it down and prove that the right triangle, triangle MCO, is congruent to the right green triangle, triangle OCD. So why those two right triangles can go into each other? First of all, they have a common side. CO is a common side that belongs to both triangles, so CO equals to itself. CO equals to CO is a common side that belongs to both triangles. In addition, side MO equals to side OD. They are both the radii of the circle, therefore they are equal to each other. Repeat again. In those two right triangles, CO equals to CO is a common side, and here side MO equals to side MO equals to side OD. MO equals to OD, they are both the radii of the circle, therefore they are equal to each other. So, by proving that the hypotenuse and one perpendicular of those two right triangles can go into each other, we actually proved that those two right triangles can go into each other. Why? Because I explained the reason that if you have an hypotenuse and one perpendicular and two right triangles that can go in, then the two right triangles can go into each other. Why? Because if we have, for example, a right triangle, triangle ABC, it is a right triangle. This is triangle ABC. And you know that the hypotenuse AC equals to 5 units and side AB, the perpendicular equals to 4 units. And here also we have right triangle, triangle DEF. With the hypotenuse DF that is also equals to 5 units, and the perpendicular DE it is also equals to 4 units. So those two right triangles can go by their hypotenuses and one perpendicular. And here, therefore, the third side mass of those two right triangles mass also can go into. Why? Because the third side, that is BC in the right triangle ABC and EF in the right triangle DEF, according to the Pythagoras theorem, the third side here BC must be equal to the square root of 5 square minus 4 square. 5 square is 25 minus 4 square, that is 16. 25 minus 16 is 9, and the square root of 9 is 3. Here also we get that EF it is also equals to the square root of 5 square minus 4 square, that is also 3. So if we have two right triangles that can go to each other by the hypotenuse and one perpendicular, then the third side must also can go into, as you can see here the third side that is BC can point to, in triangle ABC, can point to the third side that EF in triangle, that is EF in triangle DEF. Therefore, you can say that the two right triangles in our original drawing can point to each other according to side rule. Okay, so the right triangle MCO can point to the right triangle OCD according to side rule. Why? Because if you have two sides that can point, the hypotenuse on one side, then the third side must also can point. So they can point to each other according to side rule. And from the fact that can point to each other, we derive that side MC equals to side CD. Side MC equals to side CD according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can point to each other, therefore the two corresponding sides, that is to say MC and CD, must be also equal to each other. But according to what is given as the question, CD equals to 8 units. CD equals to 8 units, and from this equation MC equals to CD equals to 8, we derive that MC is also equals to 8. MC equals to 8. Here we found out that MC equals to 8 units. In the next step, I will present to you rule number 11, and we will implement rule number 11 in our drawing. According to rule number 11, if we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing, right? Because in our drawing, we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. I write it down, chord AT intersects with chord MD at point C. Point C is the intersection point. Repeat again. Now original drawing, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. I'll repeat again. According to rule number 11, we get that MC times CD equals to AC times CT. MC equals to 8 units, CD also equals to 8 units, so MC times CD is 8 times 8, that is 64. That is equal to AC. AC equals to capital R minus 2R times CT. What is the value of CT? CT equals to 2R plus capital R. Okay? CT equals to 2R plus capital R. So in conclusion, we found out that according to rule number 11, 64 equals to capital R plus 2R times capital R minus 2R. And according to the algebraic identity, that A plus B times A minus B equals to A squared minus B squared, we'll get that here capital R plus 2R times capital R minus 2R. Here A is equal to capital R and B equals to 2R. And therefore, according to this algebraic identity, that A plus B times A minus B equals to A squared minus B squared, we get that 64 equals to capital R plus 2R times capital R minus 2R will be equal to A squared. A is capital R, therefore A squared is capital R squared minus B squared. B is 2R, therefore minus B squared will be equal to minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. Minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. And we have already found out that the area of the quarter circle equals to pi times capital R squared over 4 minus the area of the small circle, that is pi R squared. Here we took pi over 4 as a common factor. Inside the brackets we have here capital R squared minus 4R squared. But we just right now found out that capital R squared minus 4R squared equals to 64. Therefore we can substitute capital R squared minus R squared here by 64. We do it now and get that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers it is equal to 50.265 square units. So we finish with the second method. In the next step, I present to you how to find out the area of the green shape according to the third method. We have already found out that CO equals to 2R, AO is the radius of the quarter circle that is equal to capital R, and we have already found out in the second method that AC equals to capital R minus 2R. We already found out that this angle equals to 90 degrees. This angle it is also equals to 90 degrees. So in the next step we will complete the quarter circle to a circle, to a semicircle. And we'll extend the radius AO until it touches the semicircle. We'll define the touching point of the extended radius AO and the semicircle as point T. Point O is the center of the semicircle, point T is the point on the semicircle itself. Therefore, OT is the radius of the semicircle that is equal to capital R. Okay, so here we'll join points T and D together by a straight line. We'll join points A and D together by a straight line. Here we extended the radius AO by a straight line. In this way, we created line segment AT. So when you extend a straight line by a straight line, the result is a straight line. Therefore, AT must be a straight line. And if AT is a straight line, we can see AT as a chord. So we have chord AT in this semicircle that passes through the center of the semicircle, and it is equal to capital R plus capital R is 2R. So any chord that passes through the center of the semicircle or the circle must be the diameter of the semicircle. So chord AT that passes through the center of the semicircle, that is to say from point O, is the diameter of the semicircle. AT is the diameter of the semicircle. And we have peripheral angle ADT. This peripheral angle ADT rests on AT, that is the diameter of the circle. And we have rule number 5 that relates to a peripheral angle that rests on the diameter of the circle. Any peripheral angle that rests on the diameter of the circle or a semicircle must be equal to 90 degrees. Here we have peripheral angle AMB that rests on AB, that is the diameter of the circle. Therefore, peripheral angle AMB equals to 90 degrees. We can implement rule number 5 in our drawing. For the number drawing, we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT must be equal to 90 degrees according to rule number 5. We define angle ATD as alpha. We define angle TAD as beta. We focus on the right triangle, triangle ADT. The right triangle, triangle ADT, angle ADT equals to 90 degrees. Therefore, the sum of the other two angles must be also equal to 90 degrees, because 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. That is to say, alpha plus beta must be equal to 90 degrees. Here in the right triangle ADT, alpha plus beta must be equal to 90 degrees. Here we subtract alpha from this equation, and we get that beta equals to 90 degrees minus alpha. We subtract beta from this equation, and we get that alpha equals to 90 degrees minus beta. So we'll focus on the right green triangle, triangle ADC. In the right green triangle, triangle ADC, this angle equals to beta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus the beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So this angle, the missing angle, must be equal to 90 degrees minus beta. But we have already found out that 90 degrees minus beta equals to alpha, therefore we can substitute 90 degrees minus beta here by alpha. Then we'll focus on the right triangle, triangle DCT, the right triangle DCT. This angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta. So we can substitute 90 degrees minus alpha here by beta. So in the next step, we'll prove that the right triangle, triangle ACD, the right green triangle, is similar to the right green triangle, triangle DCT. So write it down and prove that the right triangle, the right green triangle, triangle ACD is similar to the right triangle, triangle DCT. This right triangle. So find those two right triangles are similar to each other. First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So I write it down. This angle is angle ADC. That is equal to this angle, that is actually angle OTD, angle OTD. Or angle CTD, angle CTD. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle is angle CAD, angle CAD is equal to this angle, that is actually angle CDT. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle ACD. It is equal to this angle, this is actually angle TCD. So we actually prove that those two right triangles are similar to each other according to angle similarity rule. Triangle ACD is similar to triangle DCT according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that AC over CD equals to CD over CT. Repeat again. We derive that AC over CD equals to CD over CT. AC equals to capital R minus 2R. CD equals to 8 units. And CT equals to 2R plus capital R. So in conclusion, we found out that capital R minus 2R over 8 equals to 8 over capital R plus 2R. We will cross multiply this equation number 1, and we get that according to equation number 1, 8 times 8 is 64, that is equal to capital R plus 2R times capital R minus 2R. So according to equation number 1, 64 equals, we already found out that this expression capital R plus 2R times capital R minus 2R equals to capital R squared minus 4R squared. Okay, we found out that according to equation number 1, 64 equals to capital R squared minus 4R squared. But what is actually the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4. The area of the small circle equals to pi R squared. Here we took pi over 4 as a common factor of those two expressions. Inside the brackets we left with capital R squared minus 4R squared. And we have already found out that capital R squared minus 4R squared equals to 64. Therefore we can substitute capital R squared minus 4R squared here by 64. We substitute capital R squared minus 4R squared by 64. So this expression in total will be equal to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finish with the third method. And we finish with the second question. The next step, I'll summarize the lecture. We start with the first question, of course. So in the drawing, we have square ABCD. Inside square ABCD, we have a circle. We know that angle CBD equals to 30 degrees. Line segment PD equals to 5 units. And our mission is to find out the area of this circle. So first of all, we define the center of the circle as O. We have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We know that all the angles inside square ABCD are right angles, so this angle and the other three angles, they are all equal to 90 degrees. So inside quadrilateral AQPO, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral AQPO that has 4 right angles, it is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But we have already found out that PO equals to R. And from this equation, AQ equals to PO equals to R, we derive that AQ is also equals to R. Yeah. AQ equals to also to R. Likewise, according to the sum of the opposite sides of a rectangle are equal to each other, we get that AB equals to QO. But we already found out that QO equals to R. From this equation, AP equals to QO equals to R, we derive that AP is also equals to R. Here AP equals to R, so we found out actually that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. Okay? And we know that inside square, all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. AD equals to AB. What is the length of side AD? The length of side AD equals to R plus 5. What is the length of side AB? AB equals to R plus QB. So in conclusion, we found out that R plus 5 equals to R plus QB. We subtracted R from this equation, so R will get cancelled, and we left only with 5 equals to QB, or QB equals to 5 units. Here QB equals to 5 units. Okay? Then I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from common center point to a circle are equal. We have the common center point P. For the common center point P, we have tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. Actually, you can implement rule number 2 in our drawing. Why? If we focus on the common center point B, from the common center point B, we have tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, here BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5. So from this equation 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units here. BS equals also to 5 units. Then we join points Q and S together as straight line. In this way we created here triangle QSB. What is the size of this angle? The size of this angle equals to angle ABC, that is the right angle, minus angle CBT, that is equal to 30 degrees. That is to say, the missing angle here equals to 90 degrees minus 30 degrees, that is 60 degrees. Okay, so in triangle QBS, this angle equals to 60 degrees. Therefore, the sum of the other two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. Okay, so the sum of those two angles must be equal to 120 degrees. And those two sides, they are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha. Therefore, those two angles are both equal to alpha, and alpha plus alpha must be equal to 120 degrees. Alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that angle alpha equals to 60 degrees. This is angle alpha that is equal to 60 degrees, and this angle is angle alpha that is also equal to 60 degrees. So inside triangle QBS, we have three angles that are all equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. And you know that all the sides of equilateral triangle are equal to each other. So side QB equals to side BS, they are both equal to 5 units. Therefore, the missing side, side QS, must be also equal to 5 units. Okay. Then we join points O and S together by straight line. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of the circle that is equal to R. We have the radius OS that is 1 to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then, a perfect quadrilateral, here this quadrilateral OSBQ in a new page, and you analyze quadrilateral QBOS. This is quadrilateral QBOS in the coverage of the original drawing. Those two angles are both equal to 90 degrees. This angle equals to 60 degrees. And angle QOS is the missing angle. What is the size of this angle? The size of this angle must be equal to 360 degrees. That is the sum of the angles in any quadrilateral minus the sum of the three other angles. That is to say, angle QOS equals to 360 degrees minus 90 degrees plus 90 degrees plus 60 degrees, that is 240 degrees. That is to say, the missing angle QOS equals to 360 degrees minus 240 degrees, it is 120 degrees. So we found out that the missing angle QOS equals to 120 degrees. So this angle equals to 120 degrees. Okay. Then I presented to you the law of cosines, and we implemented the law of cosines in the green triangle, triangle QOS. What is the law of cosines? The law of cosines is drawn in any triangle. According to the law of cosines, if we have a triangle ABC, that would be any triangle. The length for side AB is A units, the length for side AC is B units, and the length of side AC is C units. And the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. Then I copied triangle QOS here and implemented the law of cosines in this triangle, triangle QOS. According to the law of cosines, in this triangle, triangle QOS, we get that 5 square equals to R square plus R square minus 2 times R times cosine 120 degrees. Again, 5 square equals to R square plus R square minus 2 times r times cosine 20 degrees. So 5 squared is 25, r squared plus r squared is 2r squared. Minus 2 times r is minus 2r squared, and cosine 120 degrees is minus 1/2, so we substitute cosine 120 degrees by minus 1/2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, found out that 25 equals to 2r squared plus r squared is 3r squared. We divided this equation by 3 and found out that r squared equals to 25 over 3. And we know that the area of any circle is pi r squared. So the area of our circle is pi r squared, but we have already found out that r squared equals to 25 over 3, so we can substitute r squared in this equation by 25 over 3. We did it and we got that pi r squared is pi times 25 over 3. That is to say, we found out that the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. In the drawing, we have a quarter circle. Inside the quarter circle, we have a small circle. Line segment CD equals to 8 units. Angle ACD equals to 90 degrees. And our mission is to find out the value of the green area. We've started with the first method. We define the center of this small circle as J. JE is the radius of the small circle that is equal to R according to our definition, that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we have JF, that is the radius of the small circle that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle. Angle AOB, this angle must be equal to 90 degrees. And here AO must be the radius of the quarter circle that we defined as capital R. Those 3 things is true in any quarter circle. So here from point J we go perpendicular on CO, and we define the touching point as point T. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Inside quadrangle CETJ, the small upper quadrangle, we have one, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Then inside quadrangle, the lower quadrangle, the small lower quadrangle TJOF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So actually found out that angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. So if angle EJF equals to 180 degrees, it means that angle EJF is a straight line. And if angle EJF is a straight line, it means that EJF is also a straight line. And if EJF is a straight line, then it means that line segment EF is also a straight line. And if line segment EF is a straight line, it means that quadrangle CEOF is a rectangle. Why? Because quadrangle CEOF has 4 right angles. Therefore, it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF, but we already found out that EF equals to R plus R, that is to R. From this equation, CO equals to EF equals to 2R. We derive that CO is also equals to 2R. Here, CO equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, D is the radius of the quarter circle that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle OCD. According to the Pythagoras theorem, OD square equals to CO square plus CD square. Then OD square equals to CO square plus CD square. OD equals to capital R, therefore OD square is capital R square. CO equals to 2R, therefore CO square is 2R square, that is 4R square. CD equals to 8, so CD square is 8 square, that is 64. So in conclusion, we found out that capital R square equals to 4R square plus 64. We subtract the 4R square from this equation. We found out that according to equation number 1, capital R square minus 4R square equals to 64. And what is the area of the green shape? The area of the green shape is very easy to see from the drawing that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. What is the area of the quarter circle? The area of the quarter circle equals to the area of the circle over 4. The area of the circle is pi times capital R square. And if you divide it by 4, we get the area of the quarter circle. That is to say, the area of the quarter circle equals to pi times capital R square over 4. What is the area of the small circle? The area of the small circle equals to pi R square. So if we're going to find out that the area of the green shape equals to pi times capital R square over 4 minus pi R square. We took pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals exactly to minus pi R square. But we have only found out that capital R square minus 4R square, this expression equals to 64, so we can substitute this expression by 64. We did it and we got the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, therefore this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the first method, then I presented to you the second method. In the second method, we use the following things that we have already found out in the first method. That is to say, we already found out in the first method that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. This angle equals to 90 degrees and this angle also equals to 90 degrees. But what is the value of AC? The value of AC is AO minus CO. Again, AO minus CO equals to AC. So AC equals to AO minus CO. That is to say, AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a circle. Then we extended the radius AO by a straight line until it touches the circle at point T. Point O is the center of the big circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle that is equal to capital R. Then we extended the straight line DC by a straight line until it touches the circle at point M. When we extend the straight line by a straight line, the result is a straight line. So DM is a straight line. If we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of DM point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. So the missing angle must be equal to 90 degrees. In order to complete the sum of the angles in the lower side of MD it points C to 180 degrees, this angle must be equal to 90 degrees. So we have here two right angles, triangle DOC, and the right angle, triangle CMO. We prove that those two right angles can go into each other. Why they can go into each other? First of all, they have a common side that is CO, so CO equals to itself, and side OD equals to side MO. They are both the radii of the circle, therefore they are equal to each other. So here, CO equals to CO, and MO equals to OD equals to capital R. By proving that the hypotenuse are not perpendicular and these two right angles can go into, we prove that those two right angles can go into each other. Why? Because if we have, for example, two right angles, triangle ABC and triangle DEF, if in those two right angles we have the hypotenuse and one perpendicular that can go into, here AC can go into DF, they are both equal to 5 units, therefore they are equal to each other. And also we know that AB can go into DE, they are both equal to 4 units, therefore they are equal to each other. So if we have hypotenuse one perpendicular that can go in, then the third side must also can go into. Why? Because according to the Pythagoras theorem, the value of the third side here must be equal to the square root of 5 square minus 4 square, that is 3. So we found out that if we have in two right angles perpendicular and the hypotenuse that can go in, then the third side must also can go in. Therefore, when we proved in those two right angles that they have the hypotenuse and perpendicular that can go in, we proved actually that those two right angles can go into each other. Why? Because the third side must also can go in, and therefore those two triangles, all the sides of the first right angle can go into all the sides of the other right angle. Therefore, those two triangles can go into each other according to side rule. Okay, from the fact that they can go into each other, we derive that MC equals to CO according to the rule that corresponding sides that can go into triangles are equal to each other. So MC equals to CD, but we already found it is given as the equation that CD equals to 8 units. So from this equation MC equals to CD equals to 8, we derive that MC is also equals to 8 units. Here MC equals to 8 units. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. According to rule number 11, if we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. Repeat again, we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD equals to AC times CT. MC is 8, CD is 8, so MC times CD is 8 times 8, that is 64, and it is equal to AC. AC is capital R minus 2R, CT is capital R plus 2R. So we found out that 64 equals to capital R plus 2R times capital R minus 2R. This expression, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, we get that in the specific expression A equals to capital R, B equals to 2R. Therefore, A squared minus B squared in our specific expression, A squared is capital R squared, B squared minus B squared is minus 2R squared. So we found out that 64 equals to capital R squared minus 2R squared. That is to say 64 equals to capital R squared minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R squared over 4. The area of the small circle is pi R squared. We took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R squared minus 4R squared. But we just right now found out that capital R squared minus 4r squared equals to 64, so we can substitute capital R squared minus 4r squared by 64. We did it, and we got that in total this expression equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, found out that the area of the green shape, according to the second method, equals to 16 pi square units, so in terms of numbers it is equal to 50.265 square units. We finished with the second method, then I presented to you how to find out the area of the green shape according to the third method. In the third method, here we already found out that CO equals to 2R, AO is capital R, and we already found out in the second method that AC equals to capital R minus 2R. This angle equals to 90 degrees, and this angle also equals to 90 degrees, according to what we already found out in the previous methods. Then we completed the quarter circle to a semicircle, and here we extended the radius AO by a straight line until it touches the circle at point T. Point O is the center of the semicircle. Point T is the point of the semicircle itself, therefore T is the radius of the semicircle, that is equal to R. When we extend the straight line by a straight line, the result is a straight line. So AT is a straight line that is equal to R plus R, that is to R capital R square plus capital R square, that is 2 times capital R square. It is a straight line that is equal to 2 times capital R square, and it passes for the center of the semicircle, that is to say it passes for point O. Therefore AD must be the diameter of the semicircle. Why? Because we can see AT as a chord. We can see AT as a chord that passes for the center of a circle or a semicircle. Any chord that passes for the center of a semicircle or circle must be the diameter of the circle. Therefore AT is the diameter of the circle or the semicircle. AT is the diameter of the semicircle. Then we join points D and T together by a straight line. We join points D and A together by a straight line. In this way we created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the semicircle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle or semicircle must be equal to 90 degrees. So we have here peripheral angle AMB that rests on AB, that is the diameter of the circle. Therefore peripheral angle AMB equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the circle. Therefore peripheral angle ADT, this angle, equals to 90 degrees according to rule number 5. Then we define this angle as alpha, this angle as beta. We focused on the right triangle, triangle ADT. In the right triangle ADT, this angle equals to 90 degrees. Therefore the sum of the other two angles must be also equal to 90 degrees, because 90 degrees plus 90 degrees, that is 100, is equal to 180 degrees, that is the sum of the angles in any triangle. That is to say, alpha plus beta must be equal to 90 degrees. We subtracted alpha from this equation and found out that beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation and found out that alpha equals to 90 degrees minus beta. Then we focused on the right green triangle, triangle ACD. The right green triangle, triangle ACD, this angle equals to beta. This angle equals to 90 degrees. Therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta, but we already found out that 90 degrees minus beta equals to alpha. So we can substitute 90 degrees minus beta here by alpha. We did it, and then we focused on the right triangle, triangle CDT. In the right triangle, triangle CDT, this angle equals to 90 degrees. This angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, so we can substitute 90 degrees minus alpha here by beta. We did it, and then we proved that the right triangle, triangle ACD, the right triangle, triangle ACD is similar to the right triangle, triangle CDT. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we found out that those two triangles are similar to each other according to angle similarity rule. And from the fact that they're similar to each other, we will conclude that AC over CD equals to CD over CD again. AC over CD equals to CD over CT. AC is capital R minus 2R, CD is 8, CT is capital R plus 2R. We cross multiply this equation and found out that 64 equals to capital R plus 2R times capital R minus 2R. We've already found out that this expression equals to capital R squared minus 4R squared. So in conclusion, we found out that according to equation number 1, 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. And this again, the area of the quarter circle equals to the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R squared over 4, and the area of the small circle equals to pi R squared. We took pi over 4 as a common factor of those two expressions. Inside the brackets, we left only with capital R squared minus 4R squared. But we have already found out that capital R squared minus 4R squared equals to 64. So we can substitute capital R squared minus 4R squared here by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. So in all the three methods, we found out that the area of this green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.